2025 A-Level Combined Mathematics Paper 1 Part B, Question number 12, Part B. Part A of this same question was discussed in the previous video. Click this link at the top right if you are interested. Part B has to do with the sums of finite and infinite series. The question of Part B says, let U of R be 7R plus 4 divided by R times R plus 1 times R plus 2 and F of R be equal to A divided by R and G of R be equal to B divided by R plus 1 for R element of the positive integers, where A and B are real constants. Find the values of A and B such that U of R, as in all of this stuff here, is equal to F of R minus F of R plus 2 plus G of R minus G of R plus 1 for R element of the positive integers. And hence we are asked to show that the sum from R equals 1 up to n of U of R is equal to 9 over 2 minus 2 over n plus 1 minus 5 over n plus 2 for n element of positive integers, and then show further that the infinite series sum from R equals 1 up to infinity of U of R is convergent and find its sum. Finally, we are asked to find the value of the real constant m such that the limit as n approaches infinity of the sum from R equals 1 up to 2n of U of R plus m times the sum from R equals 1 up to n minus 1 of U of n minus R all together is equal to 18. So to start dealing with this question, what we need to do first is to find the real constants A and B. In order to do that, what we're going to have to use is this equation for U of R, this equation for F of R, and this equation of G of R, and this relationship between U of R, F of R, and G of R. Now if we substitute into here, we will write down first U of R, which is 7R plus 4. Now remember, we're writing this like this because this R sheet that we're writing in is going to be separate from actual question paper. So when we are going to answer it, we would rather have these rewritten somewhere else so that we can easily reference. You don't need to do this, of course, but it would be easier if you rewrote these things in your paper so that you could easily reference them. So U of R is 7R plus 4 divided by R times R plus 1 times R plus 2, and then F of R is equal to A over R and G of R is equal to B over R plus 1. So F of R is equal to A over R and G of R is equal to B over R plus 1. Now from what we are given, which we will actually write from equation given, we get that U of R on the left hand side, which is 7R plus 4 divided by R times R plus 1 times R plus 2 is equal to the stuff on the right, which is F of R minus F of R plus 2, which is going to be A over R, and then F of R plus 2 is going to be minus A over R plus 2. Now it's going to be R plus 2, since if F of R is equal to A over R, when you do F of A R plus 2, you're going to essentially substitute for this R here, R plus 2, which is why we get A divided by R plus 2 here. Now for the next part, G of R minus G of R plus 1 is going to be plus B over R plus 1 minus B over R plus 2. Now the reason it's R plus 2 is that G of R is equal to R plus 1. So if we want to do G of R plus 1, we need to substitute instead of R, R plus 1. Now over here, if you substitute instead of R, R plus 1, we get B divided by R plus 1, which becomes R plus 2. And therefore, we get this thing right here. Now if we simplify this down, we can see on the left hand side, we have 7R plus 4 divided by R times R plus 1 times R plus 2, and on the right side, if we simplify all of this by taking common denominator of R times R plus 1 times R plus 2, we can see that we get A times R plus 1 times R plus 2, we get minus A times R plus 1, we get plus B times R plus 2, and finally we get minus B times R plus 1, all divided by R times R plus 1 times R plus 2. Now since R is an element of the positive integers, R is not equal to 0, R plus 1 is not equal to 0, and R plus 2 is not equal to 0. Therefore this whole product here is not equal to 0, so we can cancel these two together, leaving us with just 7R plus 4 being equal to all of this stuff here. Now if we simplify down, we can see we get A of R times R squared, A of R squared, and then A times R times 2 and A times 1 times R, which is going to be plus 3AR. We're going to get A times 1 times 2, which is going to be plus 2A. We're then going to get minus a times r, so minus ar squared, and minus a times r times 1, so minus ar. We're then going to get br times r, which is going to be b times r squared. So we have plus br squared, we have plus 2br, we have minus br squared, and we have minus br. Now cleaning all of this up, we can see that by comparing r to the power of n terms, all the terms on the left should match all the terms on the right. So if we consider n equals 0, n equals 1, and n equals 2, we can get certain equations. So for n equals 0, that's going to be the constant terms. On the left hand side, we have 4. So we have 4, which should be equal to the sum of all the constant terms on the right hand side, which is going to be 2a, and that's it. There are no other constant terms on the right hand side. So 4 is equal to 2a, which immediately gives us that a is equal to 2. So we already solved a. Now for the rest of it, if we take n equals 1, we can see we have 7 times r on the left hand side. If we compare the coefficients, that's going to be 7 on the left. On the right hand side, we have 3a, which is going to be 6, but we'll write it as 3a, minus ar, so it's going to be 2a, so 2a, and then we have 2b, and a minus b, so that's just going to be b. So we can have 2a plus b. Now already this is sufficient for us to conclude that b is equal to 3, because if you substitute 2a into here, we can see that 2a is equal to 4, which means that we have 7 equals 4 plus b. Subtracting 4 from both sides, we can see that b is equal to 3. So we don't really need to check n equals 1, but we can do it anyway. On the left hand side, we get 0. On the right hand side, we get ar squared minus ar squared, and we get br squared minus br squared, which is equal to 0. So, it's not really useful. We could still write it, of course, but it's not useful. You only need to check n equals 0 and n equals 1. Now then, with that, we've proven that a is equal to 2 and b is equal to 3. So we've proven this first part here. We've found the values of a and b. A is equal to 2, b is equal to 3. So now we've completed up to here. The next part says, hence show that the sum from r equals 1 up to n of u of r is equal to all of this stuff here. Now, in order to find this, what we're going to be using is this expression for u of r that we have up here. Now you'll notice, if we consider summing from r equals 1 up to n, this expression here, this first part becomes a telescoping sum, and this second part also becomes a telescoping sum. Because if you consider r equals 1, r equals 2, r equals 3, and so on, we're going to have for r equals 1, f of 1 minus f of 3, and then later for r equals 3, we're going to have f of 3 minus f of 5. Now this positive f of 3 here and the minus f of 3 that we had when r is equal to 1 are going to cancel out. Similarly, f of 4 and minus f of 4 are going to cancel, and so on and so forth all the way up. And due to this is going to become a telescoping sum, and only the starting terms and ending terms are going to remain. Similarly, this is also going to become a telescoping sum where only the starting terms and ending terms remain. So what we're going to do is to use that fact in order to simplify our calculation, and then eventually we're going to end up with r equals 1 up to n sum of u of r being equal to all of this. So let's go down and write this down. We know that u of r is equal to f of r minus f of r plus 2, and then that bit plus g of r minus g of r plus 1. So we have this expression here. If we sum this from r equals 1 up to n, we can see we have the sum from r equals 1 up to n of u of r, and that is equal to the sum from r equals 1 up to n of all of this stuff here, which I'm going to write with the curly bracket as the sum of f of r minus f of r plus 2, and then plus g of r minus g of r plus 1. So now what we're going to do is to consider the sum as r equals 1's values, r equals 2's values, r equals 3's values, and so on, and sum them all together on the left hand side and right hand side and see what we get. So if we consider r equals 1, r equals 2, r equals 3, and I'm going to stop there, I'm going to put a couple of dots, I'm going to go down until r equals n minus 2, r equals n minus 1, and finally r equals n. On the left hand side of this sum, we're going to have u of 1, u of 2, u of 3, so on and so forth until u of n minus 2, u of n minus 1, and finally u of n. But on the right side, if we consider what we have, if we equate all of these and slowly consider what we have, for r equals 1, the sum that we have on the right hand side is going to be f of 1 minus f of 3 plus g of 1 minus g of 2. If we go to the next value r equals 2, we're going to have f of 2 minus f of 4 plus g of 2 minus g of 3. If we go to the next one, we're going to have f of 3 minus f of 5 plus g of 3 minus g of 4. Now if we continue this down, eventually at the very end, what we're going to get is f of r, so it's going to be f of n minus 2 minus f of, this is going to be f of n. We're going to have g of n minus 2 again minus g of n minus 1, since we have r plus 1 here. R plus 1 when r is equal to n minus 2 is going to be n minus 1. And then finally, if we consider the last two terms, for if r equals n minus 1, we're going to have f of n minus 1 minus f of n plus 1 plus g of n minus 1 minus g of n. And finally, for r equals n, this is supposed to be n, not r, 1. For r equals n, we're going to have f of n minus f of n plus 2 plus g of n minus g of n plus 1. Now if we consider all the terms on the right, we can see for this sum of f components, we can see that this f of 3 cancels with this f of 3. The minus f of 3 and plus f of 3 cancel. So if we add them together, we get 0. Similarly, there's going to be f of 4 here. That f of 4 cancels with this minus f of 4, giving us 0 here. So this is 0. This is also 0, and so on and so forth downward. From the other side, we can see that this plus f of n and this minus f of n would cancel, so this is going to be equal to 0. Similarly, there would be a f of n minus 1 here, so that minus f of n minus 1 and this plus f of n minus 1 is going to cancel to give us 0, and this is going to cancel to give us 0. So all the terms in the middle are going to cancel, and we're going to be left with f of 1, f of 2, and on the other side, minus f of n plus 1 and minus f of n plus 2 here. Now similarly, for the other telescoping sum, we can see here minus g of 2 here, plus g of 2 here, so they're going to cancel, give us 0. This g of 3 cancels with the minus g of 3, giving us 0, and so on and so forth all the way down. Similarly, on the other side, this g of n cancels for this minus g of n, this g of n minus 1 cancels for this g of n minus 1, and so on upward, meaning that the only terms left here are going to be g of 1 and g of n plus 1. Minus g of n plus 1. So now if we consider the sum on the left hand side, it is just the sum from r equals 1 up to n of u of r, but on the right side we can see that what we have is f of 1, we also have f of 2, so plus f of 2, we also have g of 1 over here, so I'm going to write that down, plus g of 1, and we also have minus f of n plus 1, minus f of n plus 2, and minus g of n plus 1. Now finally, if we substitute these in, if we substitute f of 1, f of 2, f of and g of 1, and then minus f of n plus 1, minus f of n plus 2, and g of n plus minus g of n plus 1, we're going to have the final answer for the sum from r equals 1 up to n of u of r, and it's going to be exactly the expression that we had up here. So now, in order to substitute, we need to know what f of n is, or f of r is, and what g of r is. So as we know, since f of r is equal to 2 over r and g of r is equal to 3 over r plus 1, we get that the sum from r equals 1 up to n of u of r is going to be equal to, now if we go around substituting, f of 1 is going to be 2 over 1, f of 2 is going to be 2 over 2, and g of 1 is going to be 3 over 2. And then as for the other side, the minus f of n plus 1 is going to be minus 2 over n plus 1, and then minus f of n plus 2 is going to be 2 over n plus 2, and minus g of n plus 1 is going to be minus 3 over, instead of r we substitute n plus 1, so we get n plus 1 plus 1, which is going to be n plus 2. So if we finally simplify this down, we can see where the sum from r equals 1 up to n of u of r being equal to, and if we add all this together, we have 2 plus 1, which is 3, plus 1.5, which is going to be 4.5, or 9 over 2. And then we have minus 2 over n plus 1, minus 2 over n plus 1. And then we have this plus this, which is going to be minus 2 minus 3 divided by n plus 2, which is going to be minus 5 over n plus 2. Now this is going to be true for n element of the positive integers. So that's going to be our answer there. If we go up, we'll see that this answer is exactly the answer that they've given up here. If we consider the answer they've given, it is the sum from r equals 1 up to n of u of r equals 9 over 2, check, minus 2 over n plus 1, check, minus 5 over n plus 2. So that is our answer, and it is true for all n element of the positive integers. So that's going to be our answer for that component. Next, we need to show further that the infinite series sum from r equals 1 up to infinity of u of r is convergent, and we need to find its sum. Now in this case, we already know the finite series. We know the series from r equals 1 up to n of u of r. So now, in order to see whether this thing is convergent and in order to find its sum, what we need to do is to take the limit of this sum as n approaches infinity. Because in that case, the thing on top here is going to approach infinity. So this is going to approach the sum from r equals 1 up to infinity of u of r. And the thing on the right side should approach that sum. Now with this, we can also see if it's convergent, because if it's not convergent, then the limit will not exist, or it will be some infinity. But if it is convergent, then the limit as n approaches infinity of the sum from r equals 1 up to n of u of r will be some finite value, and that finite value will be the sum corresponding to this thing right here, the sum from r equals 1 up to infinity of u of r. So now if we go down, we can evaluate this. So if we consider the limit as n approaches infinity of the sum from r equals 1 up to n of u of r, this is exactly what we mean by the sum from r equals 1 up to infinity of u of r. So this is equal to the limit as n approaches infinity of the sum from r equals 1 up to n of u of r, which is also equal to the limit as n approaches infinity of the expression that we found is equal to the sum from r equals 1 up to n of u of r, which is this expression right here. So we can write that this is equal to 9 over 2 minus 2 over n plus 1 minus 5 over n plus 2. So it's the limit as n approaches infinity of 9 over 2 minus 2 over n plus 1 minus 5 over n plus 2. So now if we evaluate this limit, the first part is a constant. 9 over 2 is a constant, so it remains as it is. As for the next bit, minus 2 over n plus 1 is going to become minus 2 divided by a value that is infinity. Since as n approaches infinity, n plus 1 is also going to approach infinity. So we have basically minus 2 divided by some infinity. So as this thing on the denominator approaches infinity, minus 2 over n plus 1 is going to approach 0. Now we could do this properly by just dividing top and bottom by n, in which case we can see it's clearly approaching 0. But if we do it like this, which we can, because in this case we are not too serious about the limit part, we can directly write this is equal to 0. And similarly, for the next part here, we have minus 5 divided by n plus 1, and as n approaches infinity, n plus 2 rather, and as n approaches infinity, n plus 2 is going to approach infinity. So therefore we have minus 5 divided by an infinite value, which is going to approach 0. So we have plus 0 there as well, which means that this sum is equal to 9 over 2. So now we can conclude from this that the sum from r equals 1 up to infinity of u of r is convergent, since it is a finite value. And we can also say, and its sum is this value 9 over 2. So the sum from r equals 1 up to infinity of u of r is 4.5. Now in the last part of the question, they are saying hence we need to find that the real constant m such that the limit as n approaches infinity of all of this stuff here is equal to 18. So to solve that, what we're going to do is rewrite this limit down there and consider what the sums are equal to, and then using that we're going to consider what this should be equal to, what m should be equal to. So if we go down, what we have is that, I'm going to write a horizontal line here to separate the question. We have that the limit as n approaches infinity of the sum as r goes from 1 up to 2n of u of r plus m times the sum as r goes from 1 up to n minus 1 of u of n minus r, and this is equal to 18. Now if we consider this sum here and this limit here, we can see that this limit could be broken into two pieces, since the sum of the limits is the limits of the sum. So therefore we could break it from here and write that this is equal to the limit as n approaches infinity of the first sum, which is the sum from r equals 1 up to 2n of u of r plus m times the limit as n approaches infinity of the sum from r equals 1 up to n minus 1 of u of n minus r. Now this needs to be equal to 18. Now if we consider this thing right here, the first sum is the sum from r equals 1 up to 2n of u of r. Now since n is going to infinity, 2 of n is also going to infinity, and due to that the sum here from r equals 1 up to 2 of n and the sum from r equals 1 up to n are the same thing. Now the reason for this, the thing that's important here is that since u of r is getting smaller and smaller, this sum is convergent, and therefore taking the limit up to infinity with 2n or n is the same exact thing. So we need to write here, since limit as n approaches infinity of n is equal to the limit as n approaches infinity of 2n is equal to infinity, the sum from n equals r equals 1 up to 2n of u of r as we take the limit as n approaches infinity is equal to the limit as n approaches infinity of the sum from r equals 1 up to n of u of r. They're the same thing. It doesn't matter if you sum up to 2n or n. When you take the limit as n approaches infinity, you're just adding a bunch of infinite number of terms. So due to that, these are the same thing. Now we also happen to know what this sum is equal to. This limit as n approaches infinity of the sum from r equals 1 up to n of u of r is equal to 9 over 2. Now we've sorted out this part. We know that this is equal to 9 over 2. Let's now consider the second part. We have a constant m multiplied by this limit of this sum right here. Now if we consider this sum, we can see that we have the terms from r equals 1 up to n minus 1 of u of n minus r. If we just consider writing out these terms, the sum from r equals 1 up to n minus 1 of u of n minus r, this is going to be equal to the value at r equals 1, which is going to be u of n minus 1, plus the value at r equals 2, which is going to be u of n minus 2, plus the next value, which is going to be u of n minus 3, and so on and so forth, until the last values, when r is equal to 1 less than the final answer, as in n minus 2, we're going to have u of n minus 2, since it's minus r, n minus 2 is going to be n minus n plus 2, which is going to be 2, so therefore we have u of 2 here. And then finally, for n minus 1, u of n minus 1 is going to be u of n minus n plus 1, which is going to be u of 1. So therefore, this sum here is equal to this. Now if we consider the terms in this sum, we can see we have u of 1, u of 2, u of 3, u of 4, all the way up to u of n minus 1. So therefore, this is also equal to the sum from r equals 1 up to n minus 1 of just u of r. It's the same exact thing. Now, due to this, we can, instead of the sum from r equals 1 up to n minus 1 of u of n minus r, write that this bit here, this sum, is equal to the limit as n approaches infinity of the sum from r equals 1 up to n minus 1 of u of r. Now, doing both of those changes, using both of these substitutions, we can see that therefore, the left bit here is going to be 9 over 2, so we have 9 over 2, plus m times the limit as n approaches infinity, and for the second bit we're going to replace this sum here with the sum from r equals 1 up to n minus 1 of u of r, and that's all going to be equal to 18. So the sum from r equals 1 up to n minus 1 of u of r, and that's all going to be equal to 18. Now finally, note that the sum from r equals 1 up to n minus 1 of u of r and the sum from r equals 1 up to n of u of r, as we take the limit as n approaches infinity, are going to be exactly the same. So finally we need to say, since we'll say the limit as n approaches infinity of n is equal to the limit as n approaches infinity of n minus 1, this upper thing here, this upper limit of the sum, is going to still be equal to infinity. So therefore the limit as n approaches infinity of the sum from r equals 1 up to n minus 1 of u of r is equal to the sum, actually limit as n approaches infinity of the sum from r equals 1 up to n of u of r. It doesn't make any difference, and we know that the limit as n approaches infinity of the sum from r equals 1 up to n of u of r once again is equal to 9 over 2. Now once again we're going to substitute this into here, and we can see that therefore if we substitute, we get that 9 over 2 plus m times this value of this limit here, which is 9 over 2. So m times 9 over 2 is equal to 18. Now if we divide both sides by 9 over 2, we can see that 1 plus m over m plus 1 is equal to 18. Divide by 9 over 2, which is going to be equal to times 2 over 9. So m plus 1 is equal to, if you cancel out this, we're going to get 2 times 2 is going to be equal to 4. So it's going to be equal to 4. And therefore, if you subtract 1, m is equal to 3. So hence, for our final answer for that component, we can see that m is equal to 3. And that is the final answer that we have to give in this question. So we've solved for all of this. We've found the values of a and b given that this is true and this relationship holds. We've then shown that the sum from r equals 1 up to n of u of r is equal to all of this using the telescoping sums of this sum and this sum. And finally, we showed further that the infinite series, the sum from r equals 1 up to infinity of u of r is convergent and its sum is 9 over 2. And finally, we found the value of the real constant m such that the limit as n approaches infinity of the sum from r equals 1 up to 2 of n to n of u of r plus m times the sum from r equals 1 up to n minus 1 of u of n minus r is equal to 18. And we found that m was equal to 3. So that's going to be all for this question. Finally, if we consider the answers and the awarded marks, at the start, when you equate u of r and f of r plus 2, g of r and g of r plus 1 like this and equate both sides, you get 10 marks. When you then simplify that expression down and you cancel out the denominators like this, and you get this expression right here, which can be used to make the two simultaneous equations that you can use to then find a and b, you get 5 marks. Then when you finally find a and b, for finding a you get 5 marks, and then for finding b you get 5 marks. In the next part of the question, when you use this telescoping sum in order to find the sum from r equals 1 up to n of u of r, for writing down the first 3 terms, you get 10 marks. Similarly, for writing down the last 3 terms, you get 10 marks. Now in this case, you don't really need to write anything more than the first 3 terms. You don't need, for example, need to write r equals 4 here. Similarly, you don't need to write anything more than the last 3 terms. You don't need to write n minus 3 here, because for this telescoping sum, in order to see that it's telescoping, you only need 3 terms at the start and 3 terms at the end. When you write 3 terms, you can immediately see that f of 3 is going to cancel for this minus f of 3, and then the next f of 4 would cancel for this f of 4, and so on and so forth. If you had only 2 terms, you can see that you wouldn't be able to see that this f of 3 cancels for the minus f of 3, but once you have that, you don't need any more. So for that reason, you only need to write the first 3 and the last 3. Now moving on, when you use this sum and you find that the sum from r equals 1 up to n of u of r is equal to this thing right here, and you substitute f of r and g of r into that and get this expression, you get 5 marks. When you then simplify that expression down to get the expression that's given in the question, as in this expression right here, you get another 5 marks. It is important to also say here that this works for n element of the positive integers. Now, for the next part, when you consider the infinite sum and you consider that it's equal to the limit as n approaches infinity of the finite sum, you get 5 marks. When you then apply that limit to the actual expression for the sum from r equals 1 up to n of u of r in the finite sum, you then get 9 over 2, and for getting 9 over 2 from that, you get another 5 marks. Now interestingly, after all of that, when you then say that the sum from r equals 1 up to infinity of u of r is convergent and its sum is 9 over 2, as in stating what you just showed up here, you get another 5 marks. So it appears that the statement here is also important. Now after this point, for the last part where you have to find m, for only this part right here where you find that the sum from r equals 1 up to n minus 1 of u of n minus r is the same thing as the sum from r equals 1 up to n of u of r, as in going up and going down, as in this sum right here is just this sum but the terms are in reverse, finding that you get 5 marks. Now for some reason you don't get 5 marks, this thing right here, finding that limit up to n and limit up to 2n are the same exact thing, you don't get 5 marks for that for some reason. And for the next part here, when you do this bit right here and you find that it's also equal to 9 over 2, you don't get any extra marks for that, but you do get extra marks for this. And finally, when you solve it and you get that m is equal to 3, you get another 5 marks there. So that's going to be all for this question and all for this video. I hope you enjoyed. If you have any feedback, post them in the comments down below. Thank you for watching and goodbye.